Well, hello. Welcome to lecture number 7 on LeChatlier's principle. Our learning target is designed on helping you understand how an equilibrium can shift based upon stresses that have been placed on the system. And LeChatlier's principle describes the rules that we use to govern these shifts. Because while equilibriums are cycles, they can be manipulated to favor one side or the other because they're dynamic. You can have one side of your reaction have more concentration than the other. It's just that the rate of forward and reverse has to be the same all the time. So, how can you manipulate an equilibrium if rates are equal and concentrations are constant? Well, you can shift it because they're dynamic. You can change temperature, you can change pressure, and you can change concentration by adding or removing products, and this will cause the equilibrium to shift in favor one side or the other. The cycle is not broken, it has just been shifted towards one side or the other. For example, when I had mentioned before classroom A and classroom B and the hall in between them, let's say classroom A is really, really cold. Well, the students in classroom A want to leave. They want to go to classroom B, which is really, really warm. Well, some of the students in classroom A have their jackets. They don't care if it's cold. So let's say half of them shift from classroom A to classroom B. So then at the end, classroom A's got 5 students in winter jackets, and classroom B's got 15 students in it, all in their regular t-shirts, okay? But then let's say things shift and change. Air conditioning comes on, and classroom B gets really cold, and the heat comes on, and classroom A gets really warm. Well, students from classroom B are going to migrate back to classroom A, and the equilibrium will have been shifted. As they pass each other in the hall, we've got an equilibrium. But at the end, maybe there's 15 students in classroom A and 5 students in classroom B. So that's what we've got, shifting equilibriums. LeChatlier's principle says that an equilibrium will undergo a shift to form reactants to products or vice versa if a stress is placed on the system. The shift will reestablish the equilibrium. The stresses include, I mentioned one already, heat, but adding or removing products or reactants is another one. We can add more students to a class, it gets overcrowded and some want to move to the other classroom, and vice versa, okay? Increasing or decreasing temperature, as I mentioned with the example, hot and cold classrooms, kids want to get in and get out. Some kids like a cold classroom, others do not. So some favor other sides of the reaction. And the increase or decreasing pressure, this applies specifically only to gases, would have an effect on the equilibrium. If you want the classroom analogy, all the kids that are prepared for the exam that's going on in classroom A want to stay there because they're not under pressure. All the kids that were not prepared are going to migrate out of that classroom to somewhere else, and vice versa. Maybe the kids in classroom B who are ready to take the test ahead of time move over to classroom A. And there you have it. So pressure, temperature, and amount are what changes LeChatlier equilibriums. The rule, very simple, AA. This means all equilibriums will shift away from the chemical or heat or pressure that is added. You shift away from whatever is added. You add heat, shift away from the side that contains heat. You add compound, you shift away from the side that has that compound. You add pressure, you shift away from the side that has the gas. And there you have it. Now, TT is you shift towards what is taken away. So you're going to shift toward the side of the reaction that has heat taken away from it if heat is part of the reaction. You're going to shift towards the side of the reaction that has a product or compound taken away from it. And you're going to shift toward the side of the reaction that has fewer gas molecules if you remove gas from it. Okay? Different stresses. Concentration, adding or removing a chemical will shift according to AA and TT rules, away from what you add towards what you take. Temperature, you shift according to the AA and TT rules. Energy is treated as a product or reacted, so you'll see a side that contains energy, away from the energy that's added towards the energy that's taken away. And gases, pressure, you shift away from the side that has more gas if you take away gas. And you shift towards the side that has gas if you add more. Okay, so increase pressure, shift towards the side with fewer moles of gas, decrease pressure, shift toward the sides with more moles of gas. The direction of an equilibrium can be shifted by stressing the system as described. The amounts will change based upon the stress introduced. But once equilibrium is reestablished, concentrations become constant again, and the rate forward and reverse becomes equal. So here's a couple examples that I'll write on the board. If we add H2O gas, that means we're adding more H2O, which means we shift away from what we've added. A, T, T. So we shift away from the side that has H2O. So this equilibrium will shift to the left. And the concentration of NH3, which is over here on the left side, will increase. If we add O2, we're going to add O2. We're going to shift away from what we added, and the equilibrium will shift to the right. And the concentration of NO, which is over here, will increase. Because whatever you shift toward, the concentrations increase, and whatever you shift away from, the concentrations decrease. If we add H2O gas, equilibrium will shift to the left, away from what is added, and the concentration of NO will, NO's on the right, equilibrium shifts to the left, will decrease. The arrow that I'm drawing under the reaction is the direction the equilibrium shifts, and it increases the concentrations in the direction that it points and decreases the concentrations in the direction that it's pointing away from. If we added NO, oops, I forgot to erase this, which direction will the equilibrium shift? Away from what we add, so it's going to shift left. Which concentrations would decrease? Well, NO would decrease, H2O would decrease, and heat would decrease as well, because they're on the side that the reaction shifted away from. Temperature and heat. If we add more heat, which direction would this equilibrium shift? Which concentrations decrease, which concentrations increase? So if we add more heat, we got to shift away from what we add. So the equilibrium shifts left. 2. Which concentrations would decrease? Well, everything on the right side away from what we left would be decreasing. So NO, H2O, and heat decrease. And the final, which concentrations increase? Well, whatever you're shifting towards increases. So NH3 and O2 would increase in their concentrations. Okay. Oh, pressure on a gas. Well, we got to shift when we change the pressure. If the pressure is increased, which direction will the equilibrium shift? Well, if we increase the pressure, we shift to the side away from more gas. So we shift to the right. What will happen to the concentration of CO2 aqueous? It will increase because we're shifting towards it. If the pressure is increased, which direction will the equilibrium shift? Well, that's to the right. So that question is the same, but the second part is not. What will happen to the concentration of CO2 gas? It will decrease. Okay. If the pressure is decreased, which direction will the equilibrium shift? Well, if we drop the pressure, equilibrium shifts to the side with more gas molecules. So it would shift to the left. And what will happen to the concentration of CO2 aqueous? Well, that's on the tail end of the arrow, so it'll decrease. And if the pressure is decreased, well, we know it's going to shift to the left to favor the side with more gas molecules. But what will the concentration of CO2 gas do? That will increase because the arrow is pointing to the side that is going to get increased concentrations because of the equilibrium shift. I hope I don't run out of time here. I didn't.